Hey there, and welcome to this explainer. Today, we're jumping right in to decode the foundational language of the universe, chemical reactions and equations. We aren't just going to look at the surface level stuff, like why iron rusts or how food cooks. Instead, we're breaking down the exact stoichiometric mechanics and thermodynamic shifts that drive these processes at a molecular level. We're translating the physical world into precise mathematical reality.
Here is our agenda for today. 1. Spotting reactions. 2. The language of chemistry. 3. Balancing chemical equations. 4. Combination and exothermic reactions. And 5. Types of decomposition.
Let's get right into Section 1, Spotting Reactions, Observing the Changes Around Us.
So when you're evaluating a physical change, how do you actually conclusively prove a chemical reaction is happening behind the scenes? At a microscopic level, bonds between atoms are breaking and reforming, fundamentally altering the molecular structure of the substance itself. Because we obviously can't observe these atomic rearrangements with the naked eye, we're forced to rely on macroscopic evidence to verify that a microscopic event has actually taken place.
We're essentially looking for 4 key macroscopic signs to confirm this atomic restructuring: a change in state, a color shift, the evolution of a bubbling gas, or a spontaneous change in temperature. Take the classic reaction of dropping solid zinc granules into dilute sulfuric acid. The immediate fizzing you witness, that's hydrogen gas rapidly evolving from the solution. Simultaneously, the flask becomes noticeably warm to the touch. This spontaneous release of thermal energy, combined with the gas, provides clear, physical confirmation that a chemical transformation is actively occurring right in front of you.
Moving on to Section 2, the language of chemistry, translating observations. Historically, the simplest way to catalog a reaction, like burning a magnesium ribbon in pure oxygen to produce this dazzling white flame, was to literally write a word equation. We place our initial reactants, magnesium and oxygen, on the left. The arrow indicates the vector of the chemical change, pointing directly to the newly synthesized product on the right, magnesium oxide. But while word equations accurately describe the players on the field, they kind of lack the quantitative rigor required for actual chemical analysis.
Chemists solve this by condensing the description using chemical formula, creating what's known as a skeletal equation. Magnesium plus diatomic oxygen yields magnesium oxide, or Mg plus O2 yields MgO. This notation is great because it gives us the exact chemical identity and atomic composition of the participants. However, it reveals a glaring mathematical flaw. We have 2 oxygen atoms reacting on the left side, but only 1 emerging bound to the magnesium on the right. So the skeletal equation successfully outlines the molecular framework, but the physical mass? Entirely unbalanced.
Which brings us perfectly to Section 3, Balancing Chemical Equations, the hit and trial method.
We absolutely must balance these equations to satisfy the universal law of conservation of mass, a principle championed by Antoine Lavoisier. In non-nuclear chemistry, mass can neither be created nor destroyed. This means that every single proton, neutron, and electron present at the start of a reaction has to be perfectly accounted for at the end. You can't just magically lose an oxygen atom into the void. The total number of atoms for each specific element must remain exactly the same before and after the chemical transformation.
Think of it like a basic inventory matrix to turn a complex reaction into a simple accounting problem. In the reaction of iron and water forming iron oxide and hydrogen gas, our initial tally shows 1 iron atom on the left and 3 on the right. Oxygen shows 1 on the left against 4 on the right. Hydrogen is temporarily balanced at 2 and 2, but overall, the conservation law is severely violated. We literally have a clear deficit of reactants compared to our products, meaning we must immediately balance the equation to reflect physical reality.
To resolve this, we employ an iterative process known as the hit and trial method. First, it's absolutely critical to draw conceptual boxes around our chemical formulas, because we cannot alter the internal molecular structure. Changing H2O to H2O2, for example, doesn't balance the water. It creates hydrogen peroxide, a fundamentally different and highly reactive chemical. We can only change the number of whole molecules involved. A really effective strategy is to start balancing the compound that contains the maximum number of atoms. By equalizing the oxygen first, we temporarily throw off the hydrogen, which we then balance next, finally matching up the singular iron atoms.
And through this careful, iterative process, we arrive at a perfectly balanced equation. 3 atoms of iron, 8 atoms of hydrogen, and 4 atoms of oxygen precisely match on both the left and right sides of the reaction vector. The coefficients we added, the 3, the 4, and the other 4, act as mathematical multipliers for the entire molecule. We've preserved the chemical identity of the substances while successfully adjusting the stoichiometric ratios to obey the laws of physics.
To make this equation completely robust, textbook perfect, we must append physical state symbols. Knowing whether a substance is a solid, liquid, gas, or dissolved in an aqueous solution fundamentally impacts the thermodynamics and kinetics of the reaction. Solid-state reactions often proceed much slower than those in aqueous solutions where ions can freely collide. In our balanced iron and water equation, appending a G for gas next to the water specifies that the iron is reacting with high-energy steam rather than liquid water, which dramatically alters the energy profile and activation requirements of the reaction.
All right, on to section 4, combination and exothermic reactions, 2 becoming 1.
Take a look at the reaction between quicklime, that's calcium oxide, and water. This is classified as a combination reaction because two distinct substances fuse together to form a single, more complex product, calcium hydroxide. But more importantly, this specific synthesis is highly exothermic. In chemistry, forming new chemical bonds generally releases energy. Here, the energy released by the formation of the new calcium hydroxide bonds vastly exceeds the energy required to break the initial bonds of the reactants. The result? A massive surplus of thermal energy radiating straight into the immediate environment.
Exothermic reactions govern so much of the energy transfer in our daily lives. The combustion of natural gas or methane on your kitchen stove releases immense thermal energy as highly stable carbon-oxygen and hydrogen-oxygen bonds are formed. Even the slow decomposition of vegetable matter in a compost bin continuously releases heat through microbial metabolic pathways. Perhaps most fascinatingly, cellular respiration is a highly regulated exothermic process. The controlled breakdown of glucose in the presence of oxygen releases the exact quantum of energy needed to synthesize ATP, the literal molecular currency that is powering your cells at this very second.
And finally, Section 5, Types of Composition Reactions. Breaking it down. Decomposition is the exact thermodynamic opposite of a combination reaction. Instead of fusing together and releasing energy, a single complex reactant is broken down into simpler products. Because breaking molecular bonds always requires a net input of energy, these reactions are inherently endothermic. The first method to supply this activation energy is through raw heat, known as thermal decomposition. In the industrial manufacturing of cement, for example, a massive amount of thermal energy is pumped into solid limestone to overcome its chemical stability, shattering the atomic bonds to produce quicklime and carbon dioxide gas.
But what if we introduce a direct electrical current instead of heat? Well, we trigger electrolytic decomposition. Water molecules are highly polar and incredibly stable, but running a 6-volt electrical current through them provides enough targeted kinetic energy to force a separation. The flow of electrons systematically tears the water molecules apart, driving positively charged hydrogen ions to gather as pure hydrogen gas at the negatively charged cathode, while oxygen gas simultaneously collects at the positive anode.
Finally, we have photolytic decomposition. This one harnesses the precise energy of electromagnetic radiation. Light is composed of photons, and certain photons carry the exact quantum of energy required to cleave specific chemical bonds. This is perfectly demonstrated with white silver chloride powder. When exposed to sunlight, the incoming ultraviolet photons strike the compound with enough localized energy to break the bond, leaving behind solid gray silver metal as chlorine gas escapes into the atmosphere. This exact manipulation of light-sensitive bonds is the foundational chemistry that makes traditional black and white photography possible.
We've traced the entire structural arc of chemical reactions today, from observing macroscopic phase changes in our physical environment to translating them into strict stoichiometric equations, balancing the atomic math to preserve the laws of physics, and categorizing the thermodynamic flow of energy as bonds are relentlessly broken and formed. The chemical language of the universe is constantly written all around you in these exact mathematical terms. So what mysterious chemical reaction happening around you right now will you try to decode next?